Good afternoon, everyone. While Christian did a very nice presentation on the in silico part screening and how to limit the number of experiments you end up doing to reach your final product, I will talk a bit about the experimental side of things and how you can measure the interplay between polymers and API crystallization, and how this can influence your final crystalline form, your particle habit, and can lead to amorphous solid dispersions. So just a bit about our company, Technobis Crystallization Systems. We are a company located in Alkmaar, the Netherlands. We are specializing in crystallization equipment with over 600 products in the field. And we are proud to say that 60% of top 50 big pharma companies use at least one of our pieces of hardware. About these, nothing that out of the ordinary, just small-scale parallel reactors with inline analytics, different scales from 32 reactors in parallel from 0.2 milliliters to 8 reactors in parallel for our bigger crystalline device up to 5 milliliter scale. And using these devices, you can do all sorts of research related mostly to pre-formulation and solid form screening, but also process optimization and formulation research. This is probably something you are more than familiar with. 90% of APIs are formulated as solids, either as rapidly dissolving forms, so salts, co-crystals, nanoparticles, or as high energy forms, metastable, polymers, amorphous powders, or as solutions to avoid the dissolution step altogether. But the takeaway from this is whether it's desirable or to be avoided, crystallization is a fundamental process in the pharmaceutical industry, and I think the poll showed that quite clearly. Now, the difference between the amorphous and crystalline states is the order and the energy of the structure. You can see it very clearly in powder diffractogram. Amorphous shows a broad background, while the crystalline state shows clear peaks. But the end result in the final formulation is the concentration profile over time. Amorphous forms have, of course, the spring and parachute effect, while normal crystalline stable forms have a more gradual slope. And depending on your bioavailability requirements, of course, you're usually tempted to go for something with higher solubility, higher dissolution. Now, polymers and small molecules are generally not discussed in the same sentence, unfortunately. People doing small molecule API research generally are not the same people doing polymer research. Perhaps this conference is one of the few places where both sides talk at the same table. But once you understand the interplay between the polymers and small molecules, you can do all sorts of things. You can design amorphous solid dispersions. You can design nucleation agents to have a better industrial process. You can design crystallization inhibitors and also control your crystalline form and habit. Why? Because as Christian mentioned, the same type of intermolecular bonds, so hydrogen bonds, pi stacking, determine the properties of both, whether it's an amorphous phase or a highly ordered crystalline phase. A bit about amorphous solid dispersions, the experimental side. You usually start with your excipients, with your API, you do a solvent, and then you try to obtain the high energy state by either a flash evaporation or freeze drying. Then you do an XRPT diffractogram, hope you end up with an amorphous material, do your accelerated storage conditions, and hope afterwards that you still have an amorphous material. Of course, the key here to have this step go as you want is to choose your polymer and your excipient correctly. And of course, different polymers result in vastly different properties. For example, dissolution rate. You can have a faster control, a faster dissolution. You can have controlled drug release, all as a function of your API and your polymer. But you can use polymers not only to design amorphous solid dispersions, but also to control small molecule crystallization. And one such example was done by the Master group, where they used Merrifield resin beads as heterogeneous nucleation agents in order to control the crystallization of paracetamol, acetaminophen. And in this case, they functionalized the Merrifield resin beads with various functionalities, various chemical symptoms, and measured the mean induction time, so the time taken for the sample to crystallize out at a given supersaturation. You can see that in all cases, the results are, the induction times are significantly better than your control. So you are able to crash out your API a lot more reliably and a lot faster. The beauty of this is, again, coming back to the basics, to the intermolecular interactions. If you want to do heterogeneous nucleation, you want to have your API molecule sticking to the resin surface and nucleating there. So by doing a study on the Cambridge Structural Database, looking at the experimental single crystal structures available, and looking at the various distances for hydrogen bonding between these various functionalities, we can see that the best heterogeneous nucleators here are the ones which have the strongest intermolecular bonds. So again, coming back to the first principles. A second example from the same group, which I found quite fascinating, took the same procedure, heterogeneous nucleation, using a Merrifield resin, but postulated the following: if one chemical moiety promotes heterogeneous nucleation using an insoluble resin, then by using a soluble polymer, the same chemical functionality, the same chemical moiety will lead to an inverse effect, to an inhibition of crystallization. As the polymer molecule is soluble, it will keep the API molecules from forming nuclei and growing into crystals. And in this case, two molecules were tested. You can see the insoluble Merrifield resins as solid lines, and the soluble polyacrylamide in dashed lines, on the left for pyrazinamide, on the right for hydrochlorothiazide. And you can see the supposition matches quite nicely. You have the control in black. You have then the best heterogeneous nucleators are also the best nucleation inhibitors if grafted on a soluble polymer. The same is for the second drug for hydrochlorothiazide. Again, the best heterogeneous nucleators can be the best inhibition. Can be the best crystallization inhibitors. A final example using one of our bigger equipments, the crystalline, larger scale, and this one is equipped also with cameras, so you can see in real time your particles, your crystal counts, your crystal shape and habit. A similar study, again with acetaminophen, paracetamol, where the crystal count is plotted as a function of time. Results are in triplicate for neat paracetamol and various polymer additives. Here you can see a markedly different behavior depending on your polymer additive. For example, in the absence of polymer, for the simple paracetamol, you can see a sharp increase in the number of crystals on nucleation, followed by a decrease brought on by aggregation. This process can be avoided by using specific polymers. And this, of course, can lead to better final, better powders, which can lead to a better process. From the same study, if we look at the particle habit and how the crystals grow, we can see again a difference made by the polymer additives. So if the paracetamol crystals have a simple prism habit when they crystallize directly from water, various polymers change this habit quite dramatically by adhering preferentially to certain crystalline phases. So not only can you prevent certain aspects, but you can direct your particle size and shape. So just to conclude, if there is a takeaway from this short talk, it's that the same intermolecular forces, hydrogen bonds, for example, are responsible for both crystallization and molecule polymer interactions. And once you understand this, you can start doing all sorts of interesting processes. So you can, of course, design more stable formulations with higher drug loading. You can better control your process in production. For example, if you want to reliably crystallize at a given point in your reactor, or you can also improve your formulations and control your particle size and shape. And with this, I would like to thank you for your attention.
Thank you very much. This was sharp on time. And we have a lot of questions, especially for Christian from the first, but also some for you, Dan. And what I like about the session is we combine a little bit the artificial part plus then the reality with your modelings. I would go to the Q&A. There are many in the chat. I'm not sure if we can handle them all, but I start with one. Hi, Christian. This is Alex. Nice to meet you. Thanks for sharing us your experience. What type of lipids have you taken into account?
In this field, we have several types of lipids available and considered. And we have, for example, all different kinds of triglycerides, saturated and unsaturated triglycerides, triglycerides with different chain lengths from 8 to 18, also with different degrees and configuration on the 3 chains. And we also considered natural edible oils, these natural products which are mixtures of triglycerides, like, for example, soybean oil, coconut oil, and there are millions of them available, but
name it.
We try to cover a group and as much as possible there.
Very good. And Nico says, hey Dan, I'm coming from the GMP environment. Is it possible to perform calibrations or do an SST on Technobi's products to guarantee that the results are correct?
Short answer is yes. Most of our customers work in a GMP environment. Whether calibrations are accurate and the results are correct, I would say always look at when you're dealing with crystallization, depending what are you looking at. So the solubility curves will always be the same. However, the induction times relate to a stochastic process. So the more measurements that you do, the better value you will have for the induction time.
Very good, very good. Didier wants to know, and this is a question going to Christian, how is calculated molecular interaction with polymers, the horizontal bars in the charts, and what is the scale?
Yeah, I did not elaborate very much on it. It is the thermodynamic activity of the API in the excipient. This means we calculate the activity coefficient of the API, which is a thermodynamic quantity coming from the intermolecular interactions and can also be used for phase equilibrium calculations like solubility calculations, for example. And the scale is a logarithmic scale of the activities, as they are also logarithmically proportional to the chemical potential of a mixture. And we always made the assessment in 20 weight% formulations to compare them better at a temperature of 25 degrees centigrade.
Okay, thanks a lot. Matthias Rischer would like to know that, or says solubility is only one of the parameters to be considered in amorphous solid dispersions. Have you done studies on permeability test? This is a word breaker. Permeability test as well?
No, we didn't do so. We had a look
Okay.
at the stability in particular. Yeah.
So this is potentially something to come later on.
Yeah.
Then we have do tests for strategies for moisture protection of ASD as well, are as well considered. Do they potentially extend the potential shelf life?
Yeah, possible. If we have a packaging, for example, that protects the absorption of moisture, we have locally a different relative humidity, which is lower than the one in the storage chamber, and we could replace then the humidity in the surrounding by the one in the tablet. This is the effective relative humidity, for example, only 30% instead of 75%, and this affects, of course, the shelf life and extends it.
Okay, and then I have a question for Dan from Ankur. While using polymers or resins in crystallization process, can the same be done by using solvents, oils, or other liquids?
So you can use as crystallization inhibitors, for example, or as additives for controlling particle size and shape, other small molecules.
Okay.
Of course. However, in some ways, polymers are a lot better at inhibiting, macromolecules in general are a lot better at inhibiting crystallization due to decreased kinetics. So due to their large size, they are, generally speaking, better at slowing down crystallization.
Okay. Now I'm not sure to which of you this question will go. Can crystallization rate in vivo conditions be predicted as well? I think this was for Christian.
Might be for me, yeah.
Yeah.
I mean, this is, so to say, a shelf life prediction at the most harsh conditions we can think of, namely 100% of relative humidity of water activity, and also in a state where the polymer already dissolves in the gastrointestinal fluid. Yeah, and if we replace then the storage condition by 100% water activity and maybe even higher drug load than initially stated, then we can also take this to at least estimate the crystallization rate in vivo. Yeah.
Okay, and I saw, Christian, that you have already answered some of the questions.
Yeah, I started with that. Yeah.
In the chat, so I search some other ones that are perhaps not yet answered, but I think it's still interesting. Have you done molecular interaction tests in pharmaceutical semi-solids?
Are these, for example, paste or?
I assume so. Yeah.
Mm-hmm. Yeah, we didn't do interaction tests, but it's no problem to, no obstacle with regard to the type of excipient that is there, and if it's a semi-solid, viscosity doesn't play a role as well, so it's possible in principle.
Okay, and then
there was, I think, one moisture protection. Karina Voidart. Yeah.
Exactly.
Yeah.
So I'm scrolling.
We answered that. No, there was.
Yeah, we answered that.
Yeah.
And now I'm in the chat, which is also open. So let me just. There was one, dear Christian, I did not get how you come to the strength of intermolecular interactions bar graph. Can you explain the practical side of retrieving such graph?
Yeah, this is the, as I said, the activity of the API in this mixture, and the practical application would mean that it gives us a ranking of the interactions comparing the different excipients to each other. Measuring such an activity is hard. You can measure indirectly, for example, in case of a vapor-liquid equilibrium, an activity by vapor sorption measurements. But here, as you cannot measure, for example, an API polymer sorption, this is practically not possible. You can measure the solubility. This is an indicator of the activity.
Yeah. Okay. Okay. So there are still some more questions here, but I think we will be able to answer them also during the networking sessions and the tables. So please join Dan and Christian. And I just want to quickly show you what Dan and Christian have done with their talks today. So just need to find it. So we usually do not present this, but everybody, I hope this works. Can you see that? So what we thought is we do for every speaker that shows up here, we do a little bit for sustainability. And apart from other topics, climate is a big topic that is considering all of us. So we do some, for each presentation, we plant some trees. The same is valid for Dan. I will not show your certificate, but you will get one. I hope this is fine for everybody. And with this, I would say I can hand over to the next part, which is then the networking session. So everybody use the time to go to the tables, to the booth, to the networking carousel. If you have questions to Christian and Dan, of course, you will stick around. I assume Dan will be also at the booth of Technobis. So go and see the people, exchange, and use the time together. Big thanks to everybody, and see you in a minute. Bye-bye.